Today I will present our paper Bias for Action, Video Implicit Neural Representation with Bias Modulation. I am glad that you are interested with our research. Implicit neural representation aims to learn a mapping between coordinates and corresponding signal values. Specific to video, it consumes space and time as an input and output RGB value at that coordinate. In a sense, implicit neural representation consists of multilayer perceptron combined with nonlinear activation function. INR can be interpreted as learned dictionary, where the basis function form is dictated by choice of nonlinear activation function. These observations build a fundamental of our approach. Using learnable dictionary interpretation, we explain the main working principle of our method called ActINR through a toy example. This example consists of two isotropic Gaussians. The left one moves towards stationary right one. In context of learned dictionaries, for this specific example, the spatial extent of a basis function is governed by their weights, while their locations are controlled by their biases. Our goal is to associate a local motion and sign with a motion of corresponding basis functions. Since motion of this basis is determined by their biases, we model scene motion by modulating biases. To achieve this, we assign separate biases to each time step, while sharing weights to preserve size of basis functions over time. As demonstrated in second and third column of visualization, the basis functions maintain consistent shapes while translating through separate biases to model local motion in scene. To effectively capture local motion, we employ nonlinear activation function with a compact support in our formulation. To query any frame through our architecture, we make biases continuous by modeling them with distinct INR, referred to as bias INR. For instance, in the example above, we query bias value at unseen time 1.5, which determines corresponding motion and generates the frame accordingly. This representation is highly expressive and well suited for capturing dynamic evolution. The inductive bias of our model enables state-of-the-art performance in downstream tasks such as interpolation, impinging, and denoising. In this slide, we train both previous state-of-the-art model and our method on child video by skipping every 10 frames and interpolating all unseen intermediate frames during training, while previous state-of-the-art method exhibits ghosting artifacts on child shoes. Our method is entirely free of such artifacts. This highlights our approach as an ideal choice for challenging interpolation tasks with dramatic motion. This slide, we train both best competitor and our method on noisy black swan video and evaluate model's prediction for denoising performance. Our model effectively reconstructs clean video by solely discarding noise while keeping details intact. In contrast, the previous best competitor overfits noisy video and leaves noise in its denoising predictions. We benchmark our method against the same state-of-the-art approach. As our method is both motion and discontinuity aware, it outperforms the previous state-of-the-art. Locality bias of hybrid nerve causes it to hallucinate a brown spot on dog's head, whereas our method accurately fills those areas with dog's fur.